Good morning friends, welcome back to Parnika tutorials. In this video, I want to discuss two GATE questions which came in the year 2015 and 2020 related to process state diagram. These kind of questions will help you to understand the concept in a better way. So I request everyone to watch the complete video for better understanding. First, let me discuss the GATE 2015 question. Look at the question. The maximum number of processes that can be in ready state for a computer system with n CPUs is. N CPUs means you have n number of processors. If you have n number of processors, what are they asking? The maximum number of processes that can be in ready state. They have given four options. Option A is saying n, option B is n square, option C is 2 power n, option D is independent of n. To make you understand this concept, let me discuss the 7 states in a process state diagram. Totally, we will have 7 states in a process state diagram. They are new, ready, running, terminated, wait, suspended wait, and suspended ready. Out of these 7, let me discuss about the ready state and running state. The ready state and running state will be there in the main memory. So as the main memory is limited, a ready state and running state will have a queue. So in a ready state, you will have the ready queue. What are the processes which have been created and want to run? They will be there in the ready queue. Suppose let's take the process P1, process P2, process P3 are there in the ready queue. Based on the criteria, if it is first come first serve scheduling algorithm, the arrival time will be considered to keep any one of this process into the running state. If it is a shortest job first scheduling algorithm, then we will consider the burst time. If it is highest response ratio next algorithm, we will consider the response ratio. The process which is having the highest response ratio among these three processes will be scheduled or dispatched to the running state and it will execute. Is it clear? So, if you have n number of processes which are there in the ready queue, here even let's consider not m, even you can consider m. This m value, the m value depends on the degree of multi-programming. If your degree of multi-programming is 10, then meaning is that this queue size is 10. So 10 process can be there in the ready state. But out of this 10, only one process will be dispatched to the running state if you have one CPU. If you have one CPU, meaning is that you have one processor. If you have one processor, then among these processes which are there in the ready queue, let's assume that P1 has been dispatched. So P1 can be executed. Is it clear? Are you able to understand it or not? Now what they are asking the question, if you have n such CPUs are there. If you have n such CPUs, you can say that n number of processes will be there in the running state. But can we say anything about the number of processes which are there in the ready state? No, we cannot say, because it depends on the queue size. It does not depend on the number of CPUs. So the right answer for this question is option D, which is independent of n. It always depends on the ready queue size. It does not depend on the number of processors. I hope it is very clear for you. If it is clear, let me discuss the GATE 2020 question. Look at the question. Consider the following states about process state transitions for a system using preemptive scheduling. They are asking about the preemptive scheduling. Totally, we have two types of scheduling algorithms. One is non-preemptive and another one is preemptive. I will give a clarity about them. Now they have given 4 statements. Look at each statement. A running process can move to ready state. A ready process can move to ready state. A blocked process can move to running state. A blocked process can move to ready state. These are the four statements they have given. Now what they are asking, which of the above four statements are true? They have given four options. To make you understand this concept, let me draw the process state diagram. As we discussed earlier that we will have 7 states, let me draw the process state diagram and the transitions, then you will understand in a better way. Okay, so we will have a new state, we will have the ready, running, terminated. Let me write it as ter. Due to space issues, I'm writing it as ter, terminated. And you will have wait, and you will have suspended wait, and you will have suspended ready. Okay, now any process which have been created, see, in new state the process will be under creation. Once it is created, it will be admitted to the ready state. We will have a ready queue in that process. In that queue, the process will be in the waiting. Okay, now we will have a long-term scheduler which will admit the created process into the ready state. Then we will have a short-term scheduler or any scheduling algorithm. Based on the scheduling algorithm, one process among the process which are there in the ready queue, one process will be scheduled or dispatched to the running state and it will be executed. Is it clear? Now, how much time it will execute? It depends on the what category of scheduling algorithm you are using. If you are using the preemptive scheduling algorithm and we have non-preemptive. First, let me discuss about the non-preemptive scheduling algorithm. Any process needs some burst time. Burst time means or service time is, suppose let's take that process P1 need 2 units of service time. The service time meaning is that it needs CPU for 2 units of time to complete its task. Suppose if it is a non-preemptive scheduling algorithm, once the process has been scheduled to the running state, then it will be run for 2 units of time and it will go to the terminated state. Here I am assuming that it does not require any IO time. If it requires IO time, even if it is a preemptive or non-preemptive, if any process needs IO request, then it will be gone to the waiting state, because the CPU we should not be idle. Suppose if the process which is in the running state, it needs some IO operations, then if we keep it in the running state, then the CPU will be idle, because this process is doing some IO operation and CPU is idle. We don't want to make the CPU idle. We want to utilize the CPU as much as possible. So what we will do is that process we will shift to the wait state. Then another process which is there in the ready state, we will dispatch it to the running state. Okay, once the IO operations or IO requests are completed, the process will go to the ready state. Now ready, running and waits will be there in the main memory. They have the limited memory. So if all the process need the IO operations, then this wait queue will be completed. So if the wait queue is completed, if any other process wants the IO, then it will go to the suspended wait. Once, meaning is that it is suspended state. If it is IO operations are completed or the queue is free, it can go to the wait state, or from the wait state it will go to the ready state, because finally from the suspended wait it will go to the wait and to the ready. It will never go from suspended wait to the running or from wait to running directly. Any process has requested for the IO from the running state, it will go to the wait state, and from wait state it can go to the ready state only. Similarly, if the any process has requested the IO operation and it has completed, but this queue is full. If this queue is full, then the process can be waiting in the suspended ready. Now, what is the purpose of suspended ready? Let's take that the long-term scheduler has scheduled or admitted all the process and the size of the ready queue is full. If the size of the ready queue is full and a high priority process has been admitted to the ready state, however the queue is full but it is a high priority process, we cannot deny it. So then what it will do is that high priority process will be there in the suspended ready, so we are suspending it. Is it clear? Once this queue becomes free, then the process will be resumed. So from the suspended ready state also we will come to the ready state. Now look at these four statements, what they are telling. If it is a preemptive scheduling, see, we have discussed about the non-preemptive scheduling. However, I forgot to discuss about the preemptive scheduling. Let me discuss about the preemptive scheduling. In a preemptive scheduling, suppose let's take that you have process P1, process P2, process P3 are there in the ready state. And let's assume that process P4 is currently running. Let's assume that I will discuss with respect to the shortest remaining time scheduling algorithm, which is a preemptive scheduling algorithm. The criteria for that scheduling algorithm is burst time. Let's assume that the process P4 needs 5 units of CPU to complete its task. The process P1 needs 2 units of time. Process P2 needs only 1 unit of time. Process P3 needs 6 units of time. Now what they will check is that after certain amount of time, these processes have been arrived. Now they will look at the burst time of the processes which are there in the ready queue with respect to the running queue. The P4 needs 5 units of time, whereas P1 needs only 2 units, P2 needs 1 unit, and P3 needs 6 units of CPU time. Now among P1, P2, P3, P4, which one needs less burst time? Because it is shortest remaining time scheduling algorithm. So P2 needs less burst time. Then what it will do is that it will do the context switching. P4 will be shifted to the ready state and process P2 will be scheduled to the running state. Is it clear? However, let me give another example. Let's take that these three processes need 6, 7, 8 units of burst time. Then if you look at process P4 needs less burst time as compared to the process which are there in the ready state. Then in that time, the same process will be in the running queue and it will do its operations. Unless until the process which is there in the ready queue requires less burst time as compared to the process which is there in the running queue. Is it clear? If it is so, then we will dispatch, otherwise it will be continuing. So this is about the preemptive scheduling algorithm. So they asked it is respect to the preemptive scheduling algorithm. Look at the statement 1. A running process can move to the ready state. Yes, if it is a preemptive scheduling algorithm, a process, already I have discussed, if its burst time is less than this one, then obviously we will dispatch this process from the running state to the ready state, and the process which is there in the ready state will be scheduled to the running state. So this statement is correct with respect to the preemptive scheduling algorithm. If it is a non-preemptive scheduling algorithm, it is wrong. Now look at the next state. A ready process can move to the ready state. Yes, it is absolutely. In a new state, the process is under created. Once it is created, if it is ready to execute, obviously the long-term scheduler will admit to the ready state. Yes, even this statement is correct. Now look at the statement 3. A blocked process meaning is that the process which is there in the wait state can move to the running state. It is absolutely wrong. If any process which is there in the wait state or blocked state, once the IO requests are completed, it will go to the ready state. It will not directly go to the running state. From ready state, it will go to the running state. But they are telling that it will directly move to the running state. So it is wrong. Look at the statement 4. A blocked process can move to the ready state. A blocked process can move to the ready state. That is what we are saying. So this statement is correct. So which statement is wrong? Statement 3 is wrong. Now what they are telling, which of the above statements are true? We found that 1, 2, 4 are true. Look at each option. Option A, they are saying 2 and 3, which is wrong because statement 3 is wrong. Option B is 1, 2, 3. Even this is wrong. Why? They are saying statement 3 is true, but we found that statement 3 is false. 1, 2, 3, 4. Even it is wrong. Look at the option D. 1, 2, 4. Yes, 1, 2, 4 statements are right. So for this question, option D is right. I hope you have understood how I solve this question. If you need to solve these questions, you should be good at the theory. Already I have discussed about the process state diagram in detail in one of my earlier video. If you still have any doubts, I request you to please look at that video. Still, if you have any doubts, feel free to ask me in the comment section. I will try to clear your doubts as early as possible. Thank you for watching the complete video. Have a nice day.